So this will be just a second lecture over UV Vis Spectroscopy, just to cover a few other details. So again, in the last lecture we talked about the basics of an instrument. So you have a UV source, and then you split the beam and then send one of those beams through your sample. So that would be what's called your sample beam given the symbol I. And then you have the other beam that goes through just the reference, so just the cell and the solvent that you're using. And so that's what's called the reference beam given the symbol I0. So in UV, so transmittance is defined as the sample beam intensity divided by the reference beam intensity. So if transmittance is equal to 0.01, then only 1% light comes through the sample and 99% of the light is being absorbed. So if there's no absorption, then sample beam intensity equals the reference beam intensity, so T is 1, so that would be 100% transmittance, and no light is being absorbed. So absorbance is, so when you do UV spectrum, you plot absorbance versus wavelength. So absorbance is defined as the logarithm of the reference beam intensity divided by the sample beam intensity, and so that's the logarithm then of 1 over transmittance. So absorption equals log of 1 over transmittance. So if absorbance is equal to 2, so if you did a UV and absorbance is equal to 2, then you can solve for percent transmittance, right? Just plug in and do the math. So 2 equals log of 1 over t. And if you remember how to get rid of logarithm, you take 10 to the 2 equals 10 to the log of 1 over t, and then logarithm drops out. So 10 squared equals 1 over t. And solve for t, so t is equal to 0.01. So there's only one, so if absorption is 2, then there's only 1% transmittance, so 99% of the UV radiation is being absorbed by the sample. Okay, so common solvents in UV Vis: water, ethanol, hexane, cyclohexane, basically some solvent that does not absorb in the UV region, which these do not. So less ideal solvents, something like benzene, halogenated solvents, because they absorb in the UV region. Solvents with double bonds, so aromatic solvents like benzene, triple bonds like acetonitrile, anything with a pi system. So DMF, they have carbon oxygen double bond, acetone, anything with a pi system. Heavy atoms in your solvents like chlorine, so chloroform, dichloromethane, bromine, they absorb in the UV region, and so those solvents should generally be avoided, right, unless you don't care about the UV region. If your analysis is in the visible region, then that's not so important. But if you needed to analyze the UV region because that's where your molecule of interest absorbs at, then you have to pick a solvent that's not going to absorb in the UV region. Okay, so we talked about this last time. So the key equation in UV Vis is Beer's law. Absorbance equals, so epsilon is the molar extinction constant or molar extinction coefficient, path length and concentration. So we want to take a little bit of time to talk about the molar extinction coefficient. So that is specific to a molecule. So each molecule has its own value of epsilon. So it's a constant for a molecule, and basically it indicates how efficiently a molecule absorbs UV light. So weakly absorbing compounds have extinction coefficient values of about 10 to 100, and strongly absorbing compounds have extinction coefficient values of greater than 10,000. So the factors that affect the extinction coefficient are complex. So it's a function of the chromophore, so that's the part of the molecule that absorbs the UV radiation. So it's a function of that chromophore's area. and a function of the probability that the light will be absorbed at a given wavelength. So basically epsilon is this equation, some constant times the area of the chromophore times the probability that the light is going to be absorbed. And the factors that affect probability are themselves very complex. So they're referred to as selection rules. So one factor that affects the probability of the radiation being absorbed is how well the orbitals overlap, where the electrons being transferred from one orbital to another orbital. So for example, if we take a pi bond, so if we take formaldehyde as an example, so right, if you look at the molecular orbitals, if you take two p orbitals in phase to create pi, or two p orbitals out of phase to create pi star, if you remember what those orbitals look like, right? So pi and pi star. So what's significant is they're basically in the same, so pi and pi star. Right, so they're both perpendicular to the ring. And so that's what this diagram is trying to illustrate here. So they're both perpendicular to the ring. So pi and pi star are in similar space. So the overlap between pi and pi star is good. So that means there's a high probability that an electron, so when the radiation comes in, there's a high probability that an electron can absorb it and move from pi to pi star. So the extinction coefficient for an electron moving from pi to pi star has a high probability to occur, so it's a extinction coefficient's a pretty large value. So then of course when the right wavelength or right frequency comes in, the electron in pi can absorb that energy and move to pi star to create the excited state. And so that's a favorable process because there's good orbital overlap. So there is another transition that's possible in formaldehyde, is since it has non-bonded electrons, then an electron, so N is used to represent non-bonded electrons in UV Vis discussions. So it's possible that a lone pair of electron can move to pi star, but that's not a favorable process. The probability for that to happen is low. And the reason being, well, where are the non-bonded electrons at? They're in the sigma system. They're in the sp2 orbitals, and the sp2 orbitals are perpendicular to the pi system. So there's poor overlap, right? So sp2 non-bonded electrons are in the plane of the ring. The pi system is perpendicular to the ring. So the orbital overlap between the sp2 and the pi system is poor, right? So the probability that the non-bonded electron will absorb the energy and move to pi star is low probability. Right, so you see this then in the molar extinction coefficient. So pi to pi star has a large molar extinction coefficient. N to pi star has a very low extinction coefficient. But if you took the UV Vis spectrum of formaldehyde, you see two peaks. Right, you see a peak at 165 nanometer. That's for the pi to pi star. So that's electron in pi moving to pi star. And you see a peak around 290. So that's for the electron, the non-bonded electron moving, one of those moving from the sp2 orbital. In this case, since the oxygen atom's sp2 hybridized, that would be an electron moving from that sp2 orbital to the pi star orbital. So it's at longer wavelength, so it requires less energy to promote an electron from N to pi star, but it's a less favorable process. So the signal is much smaller, much weaker. And this signal down on the UV grid, 165 nanometer, can be obscured by oxygen in the air, or if you had a solvent that absorbed in the UV region, then that can be obscured. Okay, so we talked about this last time. So if we took these two molecules, they're both C5H8. So just to try to illustrate some of the utility of UV Vis spectroscopy. So these two molecules, since they're both C5H8, they have the same molecular ion peak and mass spec. So it'd be very difficult to differentiate between these two molecules. So if I gave you a sample, a bottle, and I didn't tell you which vial contained which sample, it would be difficult using mass spectrometry to tell the difference between them, right? Unless you understood fragmentation patterns very well and you could interpret how the molecules fragment. But if you're not an expert in mass spec and you can't interpret fragmentation patterns, then you're not going to be able to figure out which is which by mass spectrometry. And it would be difficult to differentiate them between using IR spectrometry as well, unless you're really knowledgeable about IR. Because they're both alkenes, so they're going to both have the CHSP2 stretch around 3050. They both have sp3 hybridized carbons with hydrogens on them, so they would both have the 2900 signal, and they both have carbon-carbon double bonds, so they would both have a signal around 1650. Although there would be a small shift to lower wavelengths because those double bonds are conjugated. And these are isolated. So where the double bond C stretch occurred at would be slightly different, but not a lot different. So it could be difficult using IR to differentiate between those two molecules, but it would be very easy to differentiate them using UV Vis spectrometry because conjugation has a big effect on where the signal occurs at. So the isolated double bond would be at about 178 nanometer, and the conjugated double bond, you would see a signal around 217 nanometers, so easy to differentiate between them in UV Vis. So, and you could do that analysis in just a few minutes. Of course, you could also tell the difference between the two molecules using NMR because they would give very different splitting patterns. But NMR instruments are expensive, right? The cheapest instrument is about $50,000 to $60,000, and if you want a superconducting magnet instrument, then you're easily spending well over $100,000. And it's very expensive to maintain that NMR once you buy it, whereas a UV Vis instrument only costs about $10,000 to $20,000, and there's practically no maintenance to them at all other than changing a bulb out every now and then. So UV Vis can be a handy tool to an organic chemist. Of course, there's lots of other things that you can do with UV Vis as well, but if we're just talking about getting structural information about your molecule, then that's one of the things that UV Vis spectroscopy can easily do for you. So basically anything that has color is because an electron is being excited. In organic chemistry, that's typically, again, a pi to pi star transition or an N to pi star transition. If inorganic elements are involved, also metals, where you have D and F orbitals, where the D and F D orbitals are not all at the same energy, so you can see promotion of electrons from one D orbital to another. So again, an electron is absorbing energy, and that transition happens typically in the visible region of the spectrum. So a molecule with a metal in it will typically have color as well. Okay, so just as an example, so I work with porphyrins in my research, so we do UV Vis spectroscopy all the time, right? This is the basic structure of a porphyrin. Porphyrin is found in heme, it's found in chlorophyll, and of course you know that those compounds have color. And then one of the reasons why they have color is because of the porphyrin. So it has 11 double bonds in conjugation, so it absorbs in the visible region of the spectrum, right? So porphyrin NMR looks like this. You typically have the lambda max around 419 nanometer, that's what's called the Serre band. And then you have smaller absorption bands around 500 to 600 nanometer, which is called the Q bands. And porphyrins absorb light intensely, right? Their epsilon value is about 100,000 or more. So just to illustrate the significance of that, So absorption, so if we plug into this equation 100,000 for extinction coefficient, if it's in a 1 centimeter path length cuvette, and concentrations that we have to work with are typically about 1 × 10⁻⁶ molar. So because porphyrins have such a large molar extinction coefficient, we only need a very small amount of porphyrin. So in the cuvette, we typically have 3 mils of sample. The concentration is about 1 × 10⁻⁶ molar. And then if we convert mils to liters, so that means in that cuvette, we have about 3 × 10⁻⁹ moles of porphyrin. So typical mass of our porphyrins are anywhere from 700 to about 1,000 grams per mole. So if we just take 700 grams per mole, that means in that cuvette we would have 2.1 × 10⁻⁶ grams or 2.1 micrograms of porphyrin. So don't need a lot of porphyrin to observe its UV spectrum. If we contrast that to NMR, so NMR you need about 1 milligram of porphyrin per sample. So that's about 2 × 10⁻³ molar, or so millimolar concentration. So that's about 500 times as much sample that you need for NMR compared to mass spec analysis. And so NMR is only about 7.75 mils. So we need about 500 times as much sample and much less volume. So NMR samples are about 2,000 times as concentrated as UV Vis samples are for these porphyrins that we study. So we looked at this example last time, right? That's beta carotene, absorbs in the visible region of the spectrum. 454 nanometer, has 11 double bonds in conjugation. Again, the transitions that you're seeing are these pi to pi star transitions, which have huge extinction coefficients. So beta carotene has a extinction coefficient of 140,000. So you would only need very little sample to very little dilute concentration. You're going to see the color of beta carotene, and it would have a very strong, right, absorption signal. So a basic interpretation from UV Vis: if lambda max is less than 200 nanometer, then that's a non-conjugated molecule. If lambda max is greater than 200 nanometers, that's a conjugated molecule. So different groups affect where the sample absorbs at. So every time, so if we had a simple double bond and we start changing out what X is, so if you add an alkyl group, then that'll shift the wavelength to longer wavelength by about 5 nanometers. If X was an OR group, so an ether or an alcohol there, then that's going to shift it by about 6 nanometers. If it's a halogen, that's going to shift where it absorbs at by about 10 nanometers. If it's a thiol or a sulfide, so an SH or an SR, has a big effect on where it absorbs at, about 30 nanometers, and if it's an amine, then that's about a 60 nanometer shift. So alkenes, so if you put another double bond in conjugation, that shifts where it absorbs at by about 36 nanometers to a shorter, longer wavelength. Or put it in conjugation with an aromatic ring, shifts it by about 60 nanometers. Okay, so why do amines shift it so much? They have a huge, right, the resonance structures of amines are very significant, right? You can take that lone pair of electrons down to make a double bond between carbon and nitrogen and those up. So this is a very significant resonance form for amines, so they have a very big impact on where the molecule absorbs light at. So this can be a nice tool in synthetic organic chemistry. So this is a reaction that we do, for example. So we make molecules like this, where this molecule has lots of double bonds in conjugation. So here you have a nitro group in conjugation with a benzene ring. And so these molecules typically crystallize as yellow or orange compounds. So when you put them, so we do hydrogenations to reduce the nitro group to amino group. So hydrogen with palladium on carbon, solvent of ethanol. So these are nice yellow-orange solutions. And so it's easy to tell the reaction happens because when you reduce the nitro group to the amino group, there's a big shift in where the molecule absorbs light at. And so it goes from basically a yellow-orange solution. If you stop the stirring and let the palladium on carbon settle out, which is black, if you let that settle out, then you'll see that the solution turns color and it goes colorless. And so we know that the reaction is happening. You know, why such a big change in UV in the absorption? So we're going from a nitro group, which removes electron density from a benzene ring, right, to an amino group on the benzene, which pushes the electrons into the ring. So we're going to see exactly opposite effect, and so you're going to see a big change in where the molecule absorbs UV light at. Okay, so there are basically 6 different transitions for organic molecules. So organic molecules, you know, only really have S and P electrons, and so sigma, so S and P orbitals, so sigma and pi bonds, and lone pair electrons. And if you're going to promote an electron, you have to promote an electron to an empty or a partially filled orbital. You can't promote an electron to an orbital that's already full, because you can't put more than 2 electrons in any one orbital. So that means if you're promoting an electron to a partially filled or an empty orbital, that means you're promoting an electron to pi star or sigma star. So for non-bonded electrons, then that means you can promote to sigma star or pi star. Right, so you can promote from non-bonded to pi star or non-bonded to sigma star. If the electron exists in the pi bond, then you can promote from pi to pi star, or you can promote from pi to sigma star. And if the electrons are in a sigma orbital, then you can promote from sigma to a pi star or sigma to a sigma star. But the transitions that fall in the UV Vis region of the spectrum are the pi to pi star, so pi to pi star, so that one, and N to pi star, that one. So those are the only 2 transitions that you would typically observe in the UV Vis spectrum, because the other absorptions require more energy. So if they require more energy, so that's going to mean shorter wavelength, so then you're out of the UV region and into the X-ray region. Okay, so if we have this molecule, so this absorbs, you see an absorption in the UV Vis region. So what's the transition? Well, the only thing you have are non-bonded electrons N and sigma electrons. And the one that's going to require less energy is the N to sigma star. All right, so the only transitions for that molecule would be sigma, would be sigma to sigma star, or N to sigma star, and N to sigma star requires less energy. So this is an N to sigma star transition that's being observed. It's almost beyond the UV region, right? So the UV region is typically 200 to 400 nanometers. So once you get to shorter wavelength, then you're getting into the X-ray region. Okay, so UV Vis is very important in biochemistry. So we made this point, talked about this a little bit last time. So in terms of amino acids, these 4 amino acids have aromatic rings. So they have pi to pi star transitions possible. So that would be the absorption that's being observed. And so you can use this to your benefit. For example, if you wanted to purify a protein. So if you put the protein on the column, and as the protein comes off the column, you can monitor the eluate by UV Vis spectroscopy. Right? If you see no absorption, then so assuming the protein has one of these amino acids in it, then you could use UV Vis to study that protein. So you can monitor what's coming off the column if there's no absorption, and if the protein has one of these amino acids in it, then that means there's no protein coming off the column. If you see a peak, so you take a few of these drops and you monitor them by UV, and if you see a signal, then that means the protein's coming off the column. So of course you could automate columns for organic compounds this way as well, so long as the organic molecule had a double bond in it. So then you could simply use a fraction collector, collect fractions with a robotic arm to take a sample and put it in a UV Vis instrument. And if you see a signal, and then your molecules coming off the column. Okay, so lastly, just a little bit of terminology. So chromophore, so we mentioned this a little bit earlier. So that's just a characteristic piece of the molecule that absorbs UV or visible light. So you see this term bathochromic shift used all the time. So that's just a shift in absorption to a longer wavelength, so that's called a red shift. Or hypsochromic shift, so that's just a shift in absorption to a shorter wavelength, so that's called a blue shift. Right? Why red shift and blue shift? So if you know the acronym Roy G. Biv, so the colors in the rainbow in order. So red is around 800 nanometer, violet is around 400 nanometer, right? There's blue, there's red. So if it's shifting towards longer wavelength, then it's moving towards red light. And if shifting towards a shorter wavelength, then it's shifting towards blue light. Okay, that's it for UV Vis.